Before implementing PID, we need to understand our hardware and, more importantly, what our hardware can do. Let's fill in the details of this block diagram from the previous video. We'll be using this single-phase 120-volt 1-horsepower drive to control this 3,500 RPM jet pump motor. The motor is driving an old swimming pool pump I had laying around, which forces water up to some manual butterfly valves over here. This 15 psi sensor sends a 0 to 10 volt signal back to the drive so it can monitor the system pressure. That requires an external 24 volt DC supply. I added a process meter here so we can see what the pressure is while we change the speed of the motor. Since it's just a 0 to 10 volt signal, we could use a voltmeter here, but the process meter is nice because we can set it up to display PSI instead of voltage. The water is collected in a 55-gallon drum and drains to a reservoir. The intake to the pump has a check valve to keep the water from draining out when the pump's not running. We'll control run stop with a switch on digital input 1, and we'll use digital input 2 so we can switch between controlling the drive output automatically by PID or manually by us. The drive is powered from a 120 volt single-phase input through a disconnect breaker. This block diagram and this schematic, which shows the actual pin numbers, can be downloaded from a link in the description below the video. I took this block diagram and built a small demo station like this. This drive controls this motor, which drives this pump. The water goes up here to these valves and drains out the back to a reservoir, which is just a little kiddie pool. As each valve is opened, the pressure drop is sensed by this 0 to 10 volt pressure sensor, which goes back to the drive. This is the process meter that's displaying the output of that sensor. These are the two control switches, and this is the power supply I'm using to power the sensor. The CFW-300 drive does have a 10 volt output for powering sensors, but this sensor needed at least 16 volts. We have two questions to answer. First, can this system maintain 6 psi with all valves open? And second, how does the process variable, the pressure in our example, react to changes in the control output, or the motor speed? I've already entered these basic parameters for the motor, and these for the drive control, which says we're only using local mode, and it assigns the digital inputs. Now, we're not actually using analog input 1 yet, but it does default to 0 to 10 volts, so we don't need to change that. Great. With one valve open, let's switch to run mode. Okay, at 0 Hz, we basically get 0 psi. No surprise there. I'll increase the drive frequency 5 Hz, and we still don't have any pressure. 10 Hz? Nope. 15 Hz? Nothing. 20 Hz? Looks like we might finally be getting some pressure. At 25 Hz? Okay, now we're getting something. And that makes sense. A centrifugal pump needs some minimum speed to operate, right? For our system, it takes around 20 Hz to pump enough water to build up any back pressure. Let's keep going. 30 Hz. 35. 40. 45. 50. Okay, it looks like we hit our sensor's 15 psi limit, so there's no point in continuing. If we plot that, it looks like this. So it looks like with one valve open, we only need to run the motor at a little under 35 Hz to get the 6 psi we want. I repeated that exact procedure with 2 valves open, 3 valves open, and 4 valves open. Looks like with 4 valves open, our motor needs to be at a little over 40 Hz to get the 6 psi we need. Well, great! We have fully characterized our system. That is, we now know exactly what our system's capable of under all load conditions. And more importantly, we know our system can definitely maintain 6 psi regardless. And looking at these curves, we could probably even maintain 10 or 12 psi. Cool. The point is, we fundamentally understand how our system works, and that is the first key step in getting PID to work. The important takeaway here is this relationship between the control output, the motor speed, and the process variable, the system pressure in our example. Join me in part B, where we'll see how understanding this is the key to setting up PID. Click here to see all of the videos in this series. Click here to subscribe to our YouTube channel so you'll be notified when we publish new videos like this one, and click here to learn about Automation Direct's free award-winning support options.